Okay, again, just very warm welcome to the workshop here, Machine Learning for Cancer Genomics. Honestly, it was a very challenging, I should say, workshop for me to prepare some stuff because some people just come from a variety of backgrounds. Some people are here from stats departments, some people from the pharmacology, some people from the molecular genetics, and it's not easy to just capture the taste for all those people and all the participants here for the workshop. But it's a kind of a very general review of the things we're just going to cover. It's a mind map, and today we are just going to cover some, I should say, cool algorithms for machine learning, supervised machine learning. But before getting there, we are just going to explore very briefly a very interesting, I should say, visualization technique for unsupervised machine learning. And I hope that it just whets your appetite, because I hope that at the end of the workshop, you just want to explore further if you haven't done the machine learning before. I know that for some of the people who are from pharmacology departments, there are some very cool, I should say, applications. For example, they can use some type of, for example, kernel support vector machines, or I should say neural networks, to predict, I should say, the protein-protein interactions, to which is going to be very relevant to the drug design. It was a little, I should say, heavy. I was planning first to incorporate that, I should say, technique for the workshop today, but it's very heavy stuff, and I hope that for future, when we have more workshops like that, before the September, we have a workshop for protein-protein interactions, and very interesting stuff, which you can do also do that with the neural networks. And hopefully, if you get, the main focus, as you can see from this mind map, is going to be about, as I said, supervised machine learning. But we also spend some time, which is probably sounds bizarre to you. We're just going to talk about the distance and similarity metrics, because when you will see in the future, when you just work with I should say, cancer genomics, and when you design the algorithm for that, you will notice that the choice of the distance metrics and similarity metrics is more important than the choice of the classifier and, I should say, the method which you design for the machine learning. Then we spend more time, I should say, on the distance, which you understand at the context of your work, from pharmacology to molecular genetics to the life science, which measure is more relevant for your, I should say, choice. Okay. And now, go to one of the first slides for today. I try to spend less time to talk, and we just spend more time, I should say, with coding. And if you haven't done coding, it's a good chance, because the code is already there. You can just simply play with the codes and see the impacts. Okay, today, as you know, with the high throughput, I should say, data analysis, which can be either of the DNA microarrays or protein mass spectroscopy, which we're just going to use that for protein-protein interaction, I should say, prediction and drug design. Or also, you can just have the data from comparative genomic hybridization or chromatin immunoprecipitation. For all of those data, for all of those technologies, the thing which you have is a huge, I should say, data sets which you normally are crippled to work with that, because you are doomed to deal with the concept with the curse of dimensionality. I don't know if you have heard of that or not. The curse of dimensionality, that you have, let's say, for example, the features which they exceed sometimes hundreds of thousands of the future. Have you heard of that, the curse of dimensionality? No? Now we are going to deal with that and try to reduce those dimensions to something which it makes more sense. But that's a very popular word in the literature. They call that curse of dimensionality. You work with the huge data sets, which it misleads and deceives your algorithm for machine learning. And your prediction is screwed, because the error rate which you get because of these data sets in cancer genomics, it's a challenge for that. If you work, for example, in a bank, the data sets which you get, it's very normal, the size of the data sets. You can easily have a template of the machine learning algorithm. You can just have it from a colleague, simply put the data there and just run the algorithm. And you just get the prediction with a very reasonable, I should say, prediction accuracy. But for cancer genomics, it's very challenging, because the dimension of the data sets, it cripples the algorithm which you have written. That's the thing which I think we are just going to spend some time on it today, to see how to reduce that, I should say, dimensionality, to make your prediction For cancer genomics, much more, I should say, with the high accuracy and lower error rate. That's the goal for the workshop today. Everyone is with me now? Anyone feels happy for the workshop so far? Yes.
You're talking about dimensionality, it's about the number of features.
That's right. Sometimes the number of the features goes to hundreds of thousands because every genome on the microarray you have recorded, I should say, the fluorescent intensity. And most of it is useless. You do not need them for your algorithm design. That's what we are going to today here. We are going to detect those features which is not going to be helpful to get rid of that as quickly as we can. Then we jump on to write an algorithm for that. And some of the algorithms today, you can keep it for yourself. It becomes as a template. You can always use that in future. Okay? Super. Let's go to this part. For this part, that's the framework of machine learning. Either if you are working, let's say, in a capital market at the bank, or you use that in pharmacology, or you use that, I should say, in, let's say, cancer genomics. Those steps is relevant. And we're just going to follow that. The first one is going to be the filter out. You filter out, I should say, lots of, features, which is not going to be helpful. You do not need them. That's the first step. The second step is the transformation of your data sets. You scale them. When we just work with the real data, you get to know that, what do I mean that? That's a kind of an overview. We get back to that slide more often when we go through the workshop. Then you have to select the features and the distance. The third one is very interesting because that distance is more important than the classifier of the machine learning. Then also, you have to choose your algorithm, which is that classifier. And also at the end, today we are going to assess the functionality of your algorithm. That's very important thing. It tells you how functional and accurate is your algorithm for machine learning. If you're confused now, don't worry. When we just work with the data, we get back to this slide to see which step we are now. Okay? It makes more sense in the future. Let's start with something I don't know if you have heard of not, Philadelphia chromosome. Anybody has seen that before? Yes. Yeah. It's a kind of, I should say, between chromosome number 9, you see this here, and chromosome, chromosome number 22 and chromosome number 9, when there is a genomic rearrangements from those spots which you will see there, when they just get some kind of, I should say, chemical and physical, I should say, cause behind that, they get rearranged, and instead of having a normal, I should say, chromosome number 9 and chromosome number 22, when they just get rearranged, you will see this, I should say, because of that translocation, you have two different genomes. One of them has a part of chromosome 22, and chromosome number 22 has part of the chromosome 9. That, I should say, that rearrangement sometimes is a causal effect on acute lymphoblastic leukemia, which is going to be the data sets for our workshop today. It's a causal effect for the leukemia, and now we are just going to use some machine learning to find the relevance, I should say, on these rearrangements on the cancer genomes and the genetic data which you have from microarray technology. Any questions so far? Everyone feels happy? Yeah? No questions? Great. Okay. Then let's go to your RStudio. You have on the GitHub, if you please check your email, on the GitHub you have the coding from the R. You can simply copy it from there, paste it on the RStudio. My RStudio looks, I should say, dark, the background. On the one of the tutorials, which I just emailed to you almost a week ago, I give you the instruction on how to change the appearance of your RStudio if you like that kind of background. I fell in love with that when I noticed that you can change the color of your RStudio. Okay, let's start. Everyone's happy now? Everyone has the access to the RStudio? RStudio? Yes. If you please check, I should say, to the Wi-Fi, the information is a username and password on the whiteboard. I hope that you can just read my handwriting there. Okay, and now let's start working with the data set. The data set which I'm just going to work, you're going to use bioconductor, because bioconductor, it gives you more functionality, statistical functionality compared to the R when you just work with the cancer genomics. The thing which you're going to do is that search for bioconductor, ALL installation. ALL stands for acute lymphoblastic leukemia. And installation, and I just go for the first option there, all bioconductor. I just scroll down the page, the section which is for, I should say, installation. I copy paste all those instructions in the gray, I should say, circle. And I just go back to my RStudio and copy paste it there. And I have to run it. How to do that? First of all, I just for RStudio, click on that thing. If you haven't done that with the R before, Control Enter. I just want to restart my R because I installed that before. And the bioconductor now, with that very simple, I should say, code, is installed on your R environment. And now you can just use any packages which is written specifically for bioconductor. The second line, which you're just going to use the BioC Manager, click Enter, it installs all the genotypic and phenotypic information for leukemia cancer. It's installing. It takes some time. And at the end, it will ask you if you just want to install some updates. You will see the updates. It just shows up just right there at the console there. I'm just going to click on it, press A, which stands for install all of it, press Enter. And now it's installing the updates. I hope everyone is reasonably good with the R. In case if you are not, let me know. We just go much slower. Everyone is happy to just work with the R? Everyone has done that before? Yeah, please let me know if someone has a problem with it. Okay. And now, what else do I do? When this is installed, I have to use two commands. The first one, this is like the R itself. Library. I use the command library. And inside the parentheses, I'm just going to put ALL. Control Enter. And now it's writing the ALL datasets into the R environment, back in the R. And now, still on the global environment, which is the window top, I should say right, I do not see the dataset shows up there. And the reason for it, the cure for it, is that to just write the command data, and it just pops up the ALL, and I'm just going to Control Enter, and you will see the ALL dataset shows up there at the global environment on the top right of the window. And if you are curious to see what the data looks like, and you will be surprised, you can just write the command view with capital V to show the data, to see the data, to see how it looks. And you should be very surprised because it doesn't look like a typical data set. That's one of the type of the data which you are cursed with a dimensionality. It has a phenotypic type of the data, it has a genotypic type of the data, expression, the data sets, the number of the participants, the sex, the age, everything. We do not need all of it. That's why we are just going to run this workshop, to trim it, to pre-process the data. Okay? Any questions so far? I have a good news for you. We finished the first step, which was the installation of the cancer genomic data. I think you should feel accomplished, huh? The first step is done. Okay. Before we just go to the second step, I have to remind you, those people who have just worked with the leukemia cancer cell, they know that they have two types of the cancer cell for leukemia, T-type and B-type. Those people from the pharmacology or molecular genetics should be familiar with that. They have two types. We are just going to choose only one type of the cancer, which gives us more information and more data sets. And you can check that yourself. You can just, if you, for example, on the first line, I just press ALL, the $, to find the attribute. And if I just go down there to BT, press tab, and Control Enter, you will see that at, let's say, the console on your RStudio, you have 128 patients. They have 2 levels of the cancer, either B or C, or sorry, how did I invent a C? Either B or T. And 4 classes for each, B1, B2, B3, B4, T1, T2, T3, T4. Now we are looking for those patients who have only developed B type of the leukemia cancer. That's going to be very relevant to any data sets. After the workshop today, you can just find, let's say, for example, any different type of the cancer, the kidney cancer, bless you, or any other cancer. You can just still use the same algorithms as the template to just run your work, run your machine learning algorithm. Okay, I'm just going to do that. I'm just going to run the code. I stored the code into an object which is called bcell. You can call it anything you want in case you just want to refer to that later. And I said I use the function grep, which it shows a pattern. Just search through the pattern of the patients and searches for the B. Either it can be B1, B2, B3, B4. And as a character, it searches for the ALLBT. That's the thing which we ran, and you see that there. I'm just going to run it, and you will see that on the global environment as a value you have those patients. You have, how many patients you have with the B type of the cancer leukemia? If you check at the global environment. How many patients? Yes. 95. It's very easy to find it. It's just going to be the vector here from 1 to 95. You're just going to work with 95, I should say, patients which they have developed B type of, I should say, the cancer cell. Okay. We are still in the process of, I should say, data pre-processing. We should just get to more fun stuff for machine learning. If you are getting bored, just please bear with me. Okay. And the next step, what I'm going to do, it's going to be the more fun part. That's where you are going to relate your phenotypic, I should say, data, which is B type of the cancer, that's phenotypic, to genotypic, to relate it to the Philadelphia, I should say, gene rearrangement, the slides which we had, chromosome number 9 to 22. How to find it? If you just run one of the attributes, I'm just going to write it here as a draft. ALL, the name of the data sets, $, to have the access to different features. And if I just scroll down to go to mol.bio, press tab, and Control Enter to run it. You see some magical thing happen, and you will see that I have, I should say, some patients, 100 patients to 128 patients. You see at the last line, patient 127, patient 128, and they have some, I should say, abbreviation, recognized with them. What do we mean by that? If you go back to the slide which we had, you will see that we call the mutated genome, Philadelphia chromosome, BCR-ABL. That's the medical terminology which they call that in cancer genomics. They do not call that Philadelphia chromosome. They call that BCR-ABL. Philadelphia is something more to have fun. But here, I'm just going to select those people who shows this kind of mutation. For example, patient number 1, if you look at the, shows BCR/ABL. It means that that patient which has the leukemia cancer has been diagnosed with that type of mutation, which is Philadelphia chromosome. Also, there are some other mutations. For example, ALL1, AF4, that's a different kind of gene rearrangements. Also, we have, for example, patient number 2, it's shown NEG, means negative. It means that despite the fact that he has developed or she has developed leukemia cancer, they didn't recognize any leukemia cancer for that patient. Okay? Now, you are going to select these two. We hypothesize that BCR-ABL, Philadelphia chromosome, causes the leukemia cancer, we are just going to compare that in our machine learning algorithm with patients who have no gene rearrangements, which is going to be patients which they have NEG. Huh? That's the plan. Everyone is okay with the plan? Yeah? Sorry, we are not flexible to change the plan. We have to stick with it. Okay, and now what do? I just come here. I have written a code. Let me delete my draft. Okay, go there. You see that I just called that the object which I try to create to store my, I should say, file there. I just called that gene phyla. It's easy for me to remember that in future when I want to go back to that. And I have written some stuff there. I have written here as character, which is normally, if you just run this code, what happens? I'm just going to only select this one. As you will see, I should say for the gene rearrangements, BCR, ABL, they are not as characters in the R. But if I just write the code as dot character and that object, I had to, choose both the parentheses. Just want to show what does it mean when you write the code as character. Where did it go? No worries. Let's go back to the code itself. You will see it there. And okay, and I have the pipe there with this sign in that sign. What that sign is called, by the way? I have no idea what that's called. I know only how to press it on the keyboard. Anyhow, if you just figure this out, what that sign is called, let me know before the end of the workshop. I only normally know how to just go to find it on the keyboard. And now I have created a vector there, C parenthesis. It means that's going to be a vector. I'm just going to put those two identified gene rearrangement there inside the quotation mark because I'm looking as a character. And you know, if you have A or B or anything in R, put two quotation marks in between, it means that that's a kind of a character in the R environment. I'm just going to open the quotation mark and put BCR /forward AL. Am I right? We had AL, huh? That's right. We had AL, BCR /forward ABL. And also, comma, I was going to compare that in my sample with the patients who has not developed any cancer with respect to the gene rearrangement. And control enter, and I have the object created on my global environment as a gene phyla. You can call it anything you want. You can call it apple, orange, melon, anything, but you remember that easily. Okay, and now we are getting so close to the thing which we were supposed to do. I just go back to the slide. I told you, don't worry, we are just going to go back to this slide layer. I said that we are just going to filter out. Still, we are not yet there in the chart. Now I just refer you back to that. Filter out. For filtering out, I'm just going to start doing that. You are essentially, I have to congratulate you. You are at the first step for the machine learning. Congratulations. You are doing some filtering out right now. How to do that? You have to install a package from the bioconductor. And if you please go to your Google Chrome and search for bioconductor gene filter. We are going to do lots of filtering right now. Open the window, open the link, you get to that page, which is going to be for, I should say, gene filter installation instruction. You just go to the gray area. The first code here, the if it's the installation of the bioconductor, you have done that already. No need to do that because we installed that at the very beginning. But you just go to the BioC manager. That's the thing which is going to install, I should say, R, the gene filter. I'm just going to come here, paste it. Control V, paste it there, and run it. Control Enter. And it asks me for the update. I'm just going to press A, update. Okay, and now this is installed. There is one step missing. Anyone remembers what is that step? When you install a package? I know everyone have it in there. Yes. Library. Awesome. Actually, that was it. I forgot myself. I pretended I just want to ask a question. And I asked you. Library, and I'm just going to write the same name, gene filter, control Enter, and it's going to install. Okay. Now we install it. It seems that we are ready to just write a very first code of the machine learning. Use that template all the time when you just work in machine learning to filter your gene expressions for any algorithm in machine learning. It can become a kind of a template for you. Gene filter, then the line of code which it follows. We are just going to function, I should say, with gene filter. That function is called NS filter. You see the code already there. And I'm just going to use the all filler data which I have. Oh, sorry. It seems that I forgot to run a code. If you remember, I tried to also all filler. I just skipped the code there, unfortunately. One step before, we created the gene filler, which it was, I should say, finding a vector of people with the cancer rearrangement. Yes. ABL. Oh, sorry. It should be ABL. I thought that I just corrected it. Not yet. Oh, thanks. Thanks so much. Okay, I corrected it. And now I have, I should say, 111 patients with that, I should say, gene rearrangement. Thanks. Thanks so much for reminding. Thanks. And now I'm just going to also intersect it. And what it does, it's now, if you click on that, you will see, oh my God, it seems like a catastrophe. When you click on the alpha, you see a huge, I should say, symbols, signs, which shows that you are cursed with the dimensionality. You have all kind of phenotypic, genotypic information comes with data sets for those patients who have Philadelphia chromosome. Just only for them. With the ALL, you had all the patients from T-type, B-type, all kind of rearrangements. But for all Phila, you have only those patients with Philadelphia rearrangement. It was essentially a kind of an implied filtering which we did. Now we installed the gene filter. I'm just going to go to, let's say, this all Phila NS filter. The thing which we're going to do, and that it just requires your judgment here. You are just going to solve the problem right now before we continue. When you just run the filter, I'm just going to run it with the all filler. The data sets, which you will see that this is now squared. I just highlighted it. You will see the all filler there. The intersection of all B-type cancer cells and the Philadelphia chromosome. And I have introduced something, var cutoff, variation cutoff. It severely, depending on the cutoff rate which you choose, severely filters your gene expression profile. Because you know, when you have a chromosome, when you have a gene, when you just use the microarray, you have a gene expression profiles. For example, for Philadelphia chromosome, you have, I should say, a huge, expression for the gene expressions. For the mRNA, I should say, mapping on your, microarray technology. Okay? And now, for the var cutoff, depending on the rate which you use, it depends on the power of your laptop. If the laptop you have is, let's say, it takes some computational time, normally I recommend you start from 75%. Then in that case, it just filter out, I should say, your probe data sets on the microarray experiment, and also it removes this about the less 75%, for example, of the gene expression profiles when they had the standards deviation less than that. Okay? Then, for example, you can just start from 75%, 50%. I'm just going to start, let's say, with 95%, for example, because it's going to be much faster. Otherwise, if you choose, let's say, 50%, it takes some time to filter out because it's a huge data set. I'm just going to, let's say, for example, put 95. That's for demonstration, but for sure you do not do that in a realistic situation because you are just cutting lots of things, which it doesn't make sense because you lose lots of information. But we have 2 hours for the workshop, and if you just start with, I should say, a lower cutoff rate, it may take 3 hours. Then you have to have your laptop, go home, and come back sometime soon. Yes?
So what do you want cutoff? Features?
The features which they have standard deviation less than the 95% on your, I should say, gene expression profiles. Then it's your choice. You can choose anything. You can just, for example, start with 75%. Still 75% is very stringent. It's very strict. 95% is for the sake of saving some time. Huh? And also, if you see, I have, I should say, $E set. It's always crucial as a template for you for machine learning. By doing that, you are only extracting the gene expression profiles. Because what is the plan? From the gene expression profiles, we are going to find the type of the cancer in machine learning. That's why we have $E set. Then it filters your gene expression profiles. I'm just going to click and enter. And now I'm so glad that it works. Sometimes working with bioconductor is so challenging. The function which used to work 2 minutes ago, it stops working. Okay. And now you can just take a look into the data sets by the view. And you can check the class. The class is expression set, which we are so happy. That's what we expected to have. We are looking for the gene expression profiles because the mind map is that starts from the gene expression profiles in microarrays experiment to find the cancer. From the genotypic data, go to phenotypic. That's what you do in machine learning. Okay. Any questions so far? Because we finished step number 1. And well done, everyone. Well done. You filter out lots of information. It depends on the, I hope that people choose a different cutoff rate because we're just going to go back to just work with those information which you have. And we share the information with different cutoff rates. Okay. And now I just go back to the slide. Yes.
I just tried to run the it requires like the package to
That's right. Whatever it asks you that you have to install, search it on Google, find the command line, and just run it. It happened to me a lot. Sometimes some packages it is not initially installed with the R. Whatever that install it, then just run the command. Yes.
it's different microarrays at different chip types. Do we have to install separate packages for that?
It hasn't happened to me. It doesn't matter what kind of technology you use. The algorithm is, I should say, universal for any kind of technology. Okay. Now we are going to the step number 2 to transform the data set. Any questions so far? Nothing? Then let's continue. By the way, whenever you feel exhausted, we can just have a quick break. Let me also run the package again. Everyone was able to install the package in filter? It works for everyone? Yeah?
There's something like on my Windows system that's HGU, weird.
Yeah, you have to install that package also. This is going to be for human genome datasets. Copy paste that. It comes with .db, huh?
Yeah, that'd be.
Yeah, please copy paste the whole thing. Just go to the Google, find the biopsy manager command to install it. Normally the workshops for the cancer genomics, it requires, I should say, at least a couple of days, but we are just going to have as a kind of a taster for just 2 hours. Okay. Okay, that's a package which you're looking for, huh? HGU95AV2, huh?
Yeah.
That's right. Okay. Okay, now let's go to the second step. Hopefully, just the gene filter just worked well on my, I should say, the system, because it's a very tricky, I should say, function and package. Sometimes works well, sometimes you have to rerun it. Okay, let's go to the second step. The second step is that you transform the data sets. Okay, in order to transform the data sets, we just mean that we just want to scale them, because when you just work, let's say, for example, for the data sets which you have, let me go to show that to you. If you go to, let's say, for example, go to say data, you just go to the expression, and when you run it, you will see that it shows some kind of crazy number there. Then we do not want that happens. We just want to scale the data sets which we just created. Then in order to do that, we just want to write a function in order to scale and standardize your data sets. Put every microarray expression, stand something between -1 and +1. Huh? That's the plan, which we're just going to do right now. The question? Yeah. Okay, the function which you have, I have written that for you. You can find it, I should say, on the the GitHub. The function is, in order to, I should say, put that thing on the scale. It's a very, I should say, basic concepts in statistics. For example, you just want to standardize the data sets which you have, the distribution which you have. What you do, you have your, for example, X as a kind of a samples minus any measure of, let's say, the central tendency. You can choose as a median, divided by, let's say, standard deviation or interquantile range. That's one of the basic concepts in statistics, and you use always that in cancer genomics in order to scale everything, transform everything from your microarray data into, I should say, something scalable. And in order to do that, I have written a code here, and I have written a function. The function, for example, I just put that ESET. The function's name is ESET, and it stands for raw interquantile range. What does that function do? It just goes to the matrix of, I should say, gene expression profiles, which you already filtered it to find, I should say, each row, find the median, find the standard deviation or interquantile range, and divide these two together and return it back to you. That's how you scale your function. You can always have this formula as a template. You can always use that with any context in gene expressions. And also you see that I compute, I should say, the law quantile, which is going to be the first, I should say, 25%. I'm just going to put 25% there. And also, I just find the upper quantile. I'm just going to go for the 75% of your data sets. And it seems everything is ready. And at the end, when I have measured the lower quantile with the upper quantile, 75%, 25%, I'm just going to subtract it. And that subtraction, it gives me interquantile range. Does that concept sounds familiar to you? Interquantile range? Yeah? Everyone is happy with that? Yeah? Interquantile range? Yeah. Then what I'm going to do is to run this function. And the function is readily just applied. Okay. And now, I just come to the second line. You can use that as a kind of a template all the time when you just work with the gene expression profiles to standardize or scale your microarray, I should say, gene expression profiles datasets. Based on the function which we created, I'm just going to call that this time X, because we use a different name for the functions E set, which stands for expression set. I say that whatever X is that, the function comes to subtract from it the raw medians. It's, I should say, a package. It's a function with the R for any, I should say, rows which you have in your matrix. It comes to find the median or the average of it, and divided by the raw interquantile range, which is essentially the function, and that thing which you see at the denominator, it is essentially the function which we created earlier. You will see that raw interquantile range, and I have raw interquantile range. Actually, with that function, we found, I should say, that interquantile range. I'm just going to click and run it. Okay, I hope that this line just gets, I should say, run, because 50% it works, 50% it doesn't work. Sometimes you have to restart your R to just, if it doesn't work. Hopefully this time works. Working with the gene expression profiles is not easy. Let me see that if the function is installed. Yeah, it's run it. Let's see. Okay, it just run the data sets, and as you will see, we have the gene expression profiles, I should say, installed, and we standardize it. As you see, I just called that, I store that into an option, which is called all phyla express, which is meant, this is the expression data sets. But before that, something which I do not have to forget that to tell you, otherwise I should not just forgive myself. That's crucial when you just work with the gene expression profiles, and that's the functions. This is called express. And what does it do? Whenever you just work with the cancer genomics data sets, you are confused because of the different type of the data which comes with your data sets. Using that function EXPRS, it just extracts the gene expression profiles from all the genome which is in your data sets, and I should say just exclude any other data. And that's what you want. You do not just want to just have the data sets, let's say, from the different type of the age or the sex of the patient. You just want to just work from the gene expression profiles to predict something. How you make the prediction? With machine learning or neural networks, just by way of gene expression profile. And that function is crucial because it works 50% of your way there. If you forget that function, you're screwed. Then always remember that function, express function, which extracts all the gene expression profile. We run it, and now we can also view the data sets which we had. It's going to take some time. You see that? I hope that you have, it's working much faster for you. Okay. And now we are just going to a different topic, which is, any questions so far? Anybody has been able to get the, I should say, the gene expression profile, and you can view that? Everybody succeeded to standardize your data set? And if you see your, I should say, if you see, for example, if you just go to the view of, I should say, for example, the expression profiles, you see that my laptop, it takes some time to just upload it because it's computationally very expensive. But if you just go there and see that, you see all the numbers from your gene expression profiles stands somewhere between -1 to +1. And that's what you aim for, to scale it into that predefined scale. Otherwise, your gene expression profiles gets different value from, let's say, from 9 to +2. It's all over the place. But by that code, you have it standardized. Everything stands either between -1 to +1. We just work with cancer genomics. Always, that's the crucial step to scale your information. Yes.
You want to have about 100 patients. How can you get so many rows in your data?
Because these are the gene expression profiles. 120 patients comes, let's say, at the rows. Imagine a matrix. The rows are patients. Patient X, patient Y, patient Z. But with the columns comes with that data set, thousands of the columns. Because each column shows the gene expression profiles then, from different chromosomes. And that's why the data set is inconveniently huge.
I mean, the look at the rows, a lot of rows there. So you see that there should be 1,000 rows.
Oh, if you're just looking for the gene expression, that's also, this is a kind of a variation comes with the gene expression profiles. That's why the data set is so huge.
You mean one patient will have multiple?
That's so true. That's why they call that curse of dimensionality. Your dimensions is skewed. It's so huge. Okay? And okay, now we are just going to the next step.
Excuse me.
Yes.
I'm checking the data. They find that they will all feel like express, and I still have values that are below -1.
Below -1, but this is still how far they are from minus
1.56.
That's totally fine. That's right. It should be something like that. But you do not see -2,
No.
-3. No, that's totally fine. Thanks for the question.
It could be much lower, right? Because you only use the middle from not the from max minus minimum, right?
Minus minimum, you mean? Why this is? It can.
We'll do the normalization, right? You can just minus the max value, the difference between minus and the max and minimum. Right?
Oh, you mean the normalization? That's right. That's normalization. We did the standardization. If you did normalization, that's true, but we did the standardization. They are two different. Max and mean, it's for normalization. We did the standard, but also true. If we just normalize, it also works.
Yeah, there could be some outliers where
We are going to detect the outliers by one of the algorithms. No worries about the outliers. But that's a good point. Thanks. Okay, now we are just going, I should say, to one interesting thing, which is going to be, I should say, select the distance or similarity metrics. It's going to be very crucial. We're just going to cover that when we just take a break of less than 2 minutes. Then we come back to run the first algorithm of unsupervised machine learning. Okay. There are some, I should say, some criteria for the distance. We do not have time. I'm not going to go through that because when you define a distance, it has to meet 5 different criteria. We are not going to follow that. I'm just going to show you some, I should say, the metrics for the distance. For example, we have Euclidean distance. They do not represent a physical distance. They are a measure of the similarities. If you use Euclidean distance, which it means that the square root of, I should say, differences between two objects, it doesn't mean that you're finding the distance from me to, let's say, for example, to the fan. It's a kind of a measure for similarity. Also, you have Manhattan distance. It gives you a different result. For the same cancer data sets, different, I should say, distances produces different outcomes. You have the correlation based. You have Pearson. Forget about the maths. There is no time to go there. Cosine correlation. Spearman sample correlation. And Kendall's tau. We are going to use that. It detects the outlier and kills the outlier of the samples. And Kendall tau and Spearman also, Spearman and Kendall tau, I should say, they remove the outliers. And we had also one metrics. It says Mahalanobis. It's people who are from stats. They know about that, I should say. Anybody from the stats department here from U of New York? Nobody from stats? It gives you very cool, I should say, outcome in the machine learning. We are just going to go through that. And also, that's the packages which you can find those distances. If we just want to use the tau and Spearman, you have to just go to install biodist from the bioconductor. Or if you just want to install, for example, Euclidean distance, you have to just install stats from, let's say, the R packages. And when you just install those packages, it's a matter of, I should say, a couple of seconds to find the distances and run the algorithm. Okay. Now that we are ready to just move on, unfortunately, we were planning just to spend much time on the distance because when you know what kind of distance, what kind of characteristics they have, when you just have your cancer data sets, the choice of different measurements of the distance gives you different outcomes and gives you different accuracy of your prediction. That's always, I recommend you spend more time on the distance than on the classifier algorithm. Okay, now we are just going to go to, I should say, do some cool stuff. If you just go to step number 3, we are now step number 3. What do you think if we just get 2 minutes break, then we come back to continue, huh? I see some people are yawning, and I thought that I'm boring a little, but I think that it's worth to just spend some time. 2 minutes or 3 minutes for the break. The washroom is going to be at the back, and come back. We just continue. Step number 3. Step number 3 is essentially a nice welcome to the first algorithm for KNN classification. Okay. The very interesting thing is that one part of, I should say, of my system for, I should say, gene expression, it gives me a vector with 0, I should say, identified that. It seems that I don't know what's the reason. I do not get any error message, but it doesn't pick it up for, I should say, for the gene expression profiles. It's okay. With the next step, I can catch up with you. But if you have that, I should say, the gene expression profiles, I'm just gonna just work, let's say, for example, go to this line. You can see the result. I cannot show you the result, but if you have the gene expression profile, it should work fine. Then after, we just go to write the first machine learning algorithm, which I can join you there at that step. Okay, it's going to be that step is going to be somehow an unsupervised machine learning, which by doing so, you are going to have a very interesting heat map to visualize the distances. Always remember, the measure of the distance is more important than the choice of the machine learning algorithm. For example, if you go to write a code like that, where was I? Here. If we just run a code like that, I call that Euclidean distance, EUCD. I use a function dist, which express the function which I created. You do not see that, you do not have the same function, huh? Do you have the same function or no? That's fine. Okay, whatever you have there for the distance, when you click enter, you have the Euclidean distance. You will see that it shows up at the global environment. Huh? Then the problem is that when you just want to do an unsupervised machine learning to visualize, that's a very important step. By doing, I should say, unsupervised learning, you find the genes which they cluster together, they stand close to each other, then you find a correlation between the gene which causes the cancer with the genes which you had no idea. Then it gives you a clue to do further analysis. That step is very important. That's why I told you the distance is more crucial, because it gives you some insights to some new genes which causes a cancer. In order to do that, you have to input as a matrix. Then that's what the second line does it. It converts your data sets into a matrix. That's why I call that UEM-M. It's a matrix. You can see the dimension of your matrix depending on cutoff rate. My matrix is 86 to 86 because my cutoff rate was extremely high, 99%. It means that I almost killed all the things which is my data sets. Make the things computationally faster. And now, I just want to just do some painting. That's the artistic part of the machine learning. You choose a palette because you are just going to visualize. You are just going to pick up some colors. Now you are the Da Vinci of, should say, machine learning. That's what you have to install the package. R-Color Brewer. The package is being installed. And now I just go to the library command. Everyone has a code, huh? Yeah. You run it, and now you have the palette installed. And now I call the function HMCol. It stands for heat map color. I just used color ramp palette. I just choose red and blue. Because the painting which I wanted to make, I just only choose two colors, red and blue. And my design is that if two things shows up as, let's say, red, it means that those two things are so closely related to each other. That's what the distance means. And if they are blue, it means that they are far apart. It means that they have nothing to do with each other. We do not mean a physical distance. We mean a kind of a relation. But the problem is that with this one, the palette in R is designed in a way that The higher intense, they showed it by blue. The less intensity, they showed it by red. We want it to be different. We want higher intensity to be red. And that's what I do. I just go to the HMCol, use a function as rev, HMCol. That's it only reverses. Rev stands for reverse. Reverses the design of your palette. And now if I run it, okay, if I run it, now the red shows a higher intensity and the blue shows less intensity. Okay, and now there we are to run the first algorithm for unsupervised machine learning, to visualize the distances, to figure out how the genes are related to each other. And that's the heat map function. You can use it as a kind of a template. It always runs like that. The minimal, I should say changes to that thing. I'm just gonna run it. Voila, I have this one. You can just come here to zoom it. Isn't that nice? Do you have everything? Do you see the same, I should say, the heat map, or different? Or maybe you should have a reverse one. There should be more red color there. There it is. If you reverse the color, I'm gonna zoom it, and there it is. That's the heat map, the first unsupervised machine learning. You will see, I should say, some clustering on the top. We do not talk about that because it's a very huge, I should say, concepts for the rich, I should say, cut tree, clustering, and classification. Just look at the heat map. Those areas which they have the more intense red color, it means that that's the area that you, as a researcher, you have to focus there. It's lots of things which it shows you. But the distance which we used, it was Euclidean distance, wasn't that? Huh? And look, what it happens there. I just run, I should say, I just want to use right now another package, install another package. Let me go there. Okay, and also I just missed one step. It was the Manhattan distance. That's one of the methods which we use for the distance. We just use the Manhattan distance. You can also change it to the distance of your choice. For example, you can just let me just copy paste it somewhere else. I just want to show you how the distance changes the configuration of your data sets. For the, I should say, for the distance, the method, I'm just going to write Euclidean. Control Enter. Euclidean distance. Euclidean matrix. D. And as a matrix, I'm just going to run it. And now I'm just going to come exactly do the same heat map for it. Copy paste the heat map. And I'm just going to use just the name of the function, EUM, and run it. EUM. Sorry, it was EUCM. Of the matrix. EUC mat. Full data set. And you will see that if you run it, you see exactly the same heat map because Euclidean and Manhattan sometimes are exactly the same. But now the more fun part starts with, I should say, with Tau Kendall and Spearman correlation. If you please go over there and just install the biodis package. You see all the package there, huh? And just run the library. It also asks me for the update. I'm just going to run for the updates. And just run the library, Control Enter, and to just run the library. Okay, and now just come over there. Look at that, for the Spearman correlation method. I'm just going to measure the distance based on the Spearman, which is, it finds not the distance between two genes, it just finds, I should say, the correlation which they have. And that's why in cancer genomics, normally that Spearman or the Ken delta are more relevant. I'm just going to run the function, convert it into the matrix, and just run the heat map. Wow, look at that. Your heat map looks much way different from the one which you had before. If you zoom it, you will see a different, I should say, pattern. Everyone see the same thing or different? It's running? Because how much was the cutoff rate? If your cutoff rate it was not 95%, probably the computation, it takes more time for you. That was the reason I just chose 99, because I just wanted to run everything so fast. Okay. And now, I'm just going to show you something very crucial. There is a function which it finds, look at that, it comes after the heat map functions, because when you just run the heat map, if you have, let's say, the cutoff rate, the cutoff variance which you had, if you, for example, run your algorithm on the whole data sets, looking at the heat map is very confusing. You see thousands of genes are clustered, and you do not know which gene relates to the gene of your interest. There is a function there, this is called closest.top. Huh? For example, you just come with an ID of the gene. Later you will see that you can change this ID of the microarray into a symbol of the gene. We have a command layer coming up. That's going to be your gene of interest. And you say that it's going to search for, by the way, for any commands, if we just put your cursor before the parenthesis, press F1, it opens the help menu for there. And you see what kind of arguments you have to put inside the function. Just pressing F1 when you put the cursor before the parenthesis. And you see that for the first argument is the X, which essentially is a gene of your interest. The second argument is a distant matrix. Dist.mat means a matrix which you created. We created, I should say, the Spearman matrix, which is Spear M. And the top means the number of the genes which in your heat map comes as close as to your gene of interest. For example, if that gene 39120_AT, you can choose anything else from your heat map. Look at your heat map, pick up something, put it there. When I just put 1, and when I enter it, it shows me that thing, gene number 36821_AT. It means that that gene, based on the distance which you measured as a Spearman, stands as close as to your gene of interest as possibly. Means that it has the highest correlation based on the distance which you selected as a Spearman. If you choose, let's say, Euclidean distance or Manhattan, you get a different result. And that's why I told you, the choice of the distance, it changes the protocol of your research. Because you may find a different gene when you choose a different distance, and it may lead you somewhere else. That's why always ask yourself, when you do machine learning in genomics, what distance measure you have to choose. We're just going to go for the last one. It's going to be tau d. I'm just going to control D. That's a tau Kendall. Change it to the matrix. Run the heat map. And you see the heat map is more severe. And now the gene of the interest. You see that I got a gene and coincidentally, for this one, Kendall and Tao, they just got something similar for me because I had very, I should say, a huge cutoff rate. But for you, it should be different. Each distance gives a different genome, which it comes close to the thing which you had measured. We have two more distances, Hamming distances and Kullback-Leibler distances, which is very interesting distances in statistics. I'm not going to cover that. We're running out of the time. Then please, when you get back home, simply control it on those things. I post the slides. You educate yourself of those two distances. They are the best distances in cancer genomics, but we have to just skip them to get to some more fun stuff. We had also a kind of a projection technique, which it shows your gene from that huge dimensions into 3 dimensions. You can use your cursor to move around to see how genes are closely related to each other. Simply when you just got home, just run them. The package for that is MASS. You see the package MASS and RGL. Run those packages, just run those codes. You see a very fun stuff to play around with. You can visualize the genes in 3D to see how they are closely related to each other. I'm just going to skip that to just in order to just get to the first algorithm for machine learning. Sorry if I had to skip. 2 hours for machine learning for cancer genomics is crazy. It requires days, weeks of working them. But that's the kind of a taste to see how it works. Okay. We are going to step number, I should say, I'm going to go back to our roadmap. We choose the distance, and now we are just going to select the features. That's what we are going to do. Please, yes.
Yeah, how do you choose this? You get try them all and pray?
It depends on your experiment. You have to come with your experiment to see what does it mean if 2 items are similar. Then based on that, it means that, for example, if they show a higher correlation. For example, if your experiment, sometimes you have to use Kullback-Leibler, I should say, information distance, because you just want to see how those distribution are closely related, not the correlation, the distribution of those expressions. Then it depends on your, I should say, experiment. And to be clear with yourself, what does it mean if two genes are similar? Because distance always shows similarity. And wrong choice of distance takes you somewhere which should not be there. That's very crucial. That's always I emphasize. The distance measure is more important than the classifier itself.
So you have to rely on your domain knowledge.
Absolutely. When you just work in finance or bank, always you can use Euclidean distance because that's the handy distance. You do not need to find the correlation. But for cancer genomics, it's a very tough one because you have to have lots of domain knowledge to see what does it mean when 2 genes are closely related. Huh? Make sense? Super. Okay, now please scroll down to the section which it says Supervised Machine Learning Data Splitting. Okay, and now the thing is that's a kind of a general, I should say, approach. When you have the machine learning, you always, for example, it's like you are having a dinner, you have a plate, you do not eat it all. You split your dinner on your dish, you eat 2/3 of your food, and leave 1/3 for future, for your tomorrow breakfast, for example. Huh? That's exactly like machine learning. You split your data on your plate 2/3. With 2/3 of your data, you train your system. With 1/3 of your data, you try to see the prediction that you made, how efficient is that, how accurate is that, based on the 1/3 of your data. That's the general rule for machine learning. Huh? And that's what we are going to do. We do not follow the approach of 2/3 to 1/3. We are just going to make some samples. The first line of code. Next, if I run it, it shows the items which they have no cancer rearrangement. The second line picks the items with the Philadelphia chromosome rearrangements. The sample 1 makes a random sample of your, I should say, NIC data sets to pick up only 22 items from there. It says sample next. 22 means 22 items from your sample, and replace false. You make your first sample. The second sample, it picks up random 22 item from, I should say, your BCR item from the Philadelphia chromosome. And what do? Now I make my training set by combining them together using the C command. And that one is there. I created my training set. This is my 2/3 of the food for tonight. 1/3 for the breakfast tomorrow comes here with the test set. But I use a function set difference. 1 to 80 means that 1 to 80, whatever is left, it takes it to the test set of your training set. Now we created training set and the test set. Now we know what's going to happen next. Everyone is cool now? Everyone's happy so far? You are moving so fast to run the first algorithm of machine learning. One of the things which I have to remind is that for cancer genomics, R is the best package for machine learning because some of the features for genomic data comes with the R which doesn't come with the Python. For example, the package which I have here, maybe you do not have it there. It's ML interfaces. ML interfaces comes only with the R. And you will see that how easy is that to use that package. Everyone has that command there in your, I should say, your workbook? ML interfaces? Everyone has it? Yeah. Okay. Then I'm just going to run it. It means machine learning interface. It's running the package. Any questions so far? As long as it's just installing the updates. Just going to also run the library. Okay, and now look at that. I have to congratulate you so warmly because now you are writing the first algorithm from machine learning, K&N algorithm. How it works? This is the fastest, I should say, training with the machine learning. We do that as quickly as we can. Look at that, how K&N works. K nearest neighbor. That's what it stands for. It means that, for example, look at the graph over there. Look at the star. At the star, that's the thing which you have no idea what is that. You have two different samples. You have the purplish, I should say, circles. You have the yellow ones. And the star in the middle, you have no idea if this is purple or if this is yellow. Which one you think is that? What is your best guess? Is it purple or it is yellow? For our purpose, purple can be Philadelphia chromosome, yellow can be no gene rearrangement. Which one you think? What is your best guess for the star?
Depends on the value of K.
Depends on the value of the K. K there is 3, for example. That was very good. The value of the K. Super. Brilliant. But the thing is that if we choose value K equal to 3, means that we have a radius of, let's say, 3 around, I should say, your star. 3 means 3 nearest neighbors. When you have 3, look at that. How many neighbors you find there? Then 3. You search for the 3 closest neighbors. 1, 2, 3, they are the closest in that radius. And you find the probability. You see that the star, when K is 3, it is close to 2 purple, 1 yellow. You take the votes from it. 2 purple, 1 yellow. Then your classifier algorithm, machine learning, decides, then the star is going to be purple. Because there are more votes from the purple than yellow. It's called a kind of a Bayesian statistics. We do not go through the math, but that's how it is. You take the higher votes of the closest neighbors. It's like you are friends with good friends. The more friends you have, they are good. There is a chance that you are a better personality. That's like that. But if K is 6, what is your guess? By the way, I just got that from, I should say, the slide from the Wikipedia. I'm not gonna do plagiarism. that's I have to mention. But if your K is 6, as you mentioned, that it depends on the number K, what do you think then in that case? Is a star is purple or yellow? Take the majority votes. Find 6 closest neighbors. Going to be 1, 2, 3, 4, 5, 6. Star is yellow or purple? K equal to 6. Who says yellow? Who says purple? That's yellow. Because you see that you have, I should say, 5 yellow and 2 purple. That's the majority vote. And you see, that's a good lesson to take. Depending on the K which you choose, your diagnosis of the star is different. If K was 3, the star was supposed to be purple. If K is 6, your star is supposed to be yellow. Then imagine that you are diagnosing someone with a cancer. If K is 3, you diagnose that person to have cancer tumor, but if you choose K6, then you say, that person is completely healthy. Then you see the dilemma here for machine learning. Depending on the K, you have different results. Any question on the K and N? No questions so far? Everyone is happy with the concept? Okay. And now you know the concept, that's time to just put that into some codes to see how it works on the cancer genomics. Okay. We are just going to run the first code of the K and N. And that's the code. I call the algorithm KNN1. KNN1. And you can call it anything. I use a function mlearn. It stands for machine learning. It comes only with the R, not with the Python. And if you do not know what kind of arguments it has to go there, press F1. You see it there. The first argument comes as formula. If you check the formula, the help package there. The formula is that you come for the class. What are we trying to predict is the class. If you remember, the mol.bio was the type of, I should say, the gene rearrangement. Philadelphia chromosome, neg, ALF4, those kind of stuff. That's what we are predicting. That's a class. That's, for example, in the KNN, it's going to be, let's say, that yellow or purple, I should say, circle. Then you say that the class, I have that sign. I do not know what that is called. That curly, I should say, eh? I know where is that on the laptop. If you know what that's called, just let me know. Tilde, yeah. Tilde. Tilde, and I have a dot there. It's very crucial. Dot means that your function y, mol.by is like the y, equals to x. It means that your y, your prediction, mol.by is your prediction. It can be anything when you just do the machine learning. It's a general rule. Your prediction equals to everything. You do not know anything about your futures. You put a dot there and you relieve yourself. Okay, whatever it can be. I do not bother myself to search for the future. Then comma. The next argument is a data. Your data is what you filtered out before. Fila. And dot method. And dot method there. It's going to be, when you use ML interfaces, the name of the package comes with I at the end. For example, random forest, with the machine learning interfaces come with random forest I. K and I. And you choose K. You choose L equal always to 0. But for the K, that's what we meant. K equal to 3 was yellow. Purple, K equal to 6 was yellow on that slide. And that's the K we should choose. You can work with it to find the optimal, I should say, precision. We just put it 1. You can change it with 2, 3, or anything. K means the first closest neighbor. If I go back to that slide, it means that if I choose K equal to 1, it means that, for example, for that to start, the only closest neighbor, which is going to be this purple one. is taken into the account then. K equal to 1. And the fourth argument is train IND. I leave it where it is. I do not just mess around with the arguments, but I only change it with the training set which I created. And now with the training set, I'm training the machine learning to make the prediction. Everything seems okay. I'm just going to control enter. And there it is. My algorithm is run. And I wrote the first machine learning algorithm for KNN, or K nearest neighbor. As easy as that. You can always have a template. Whenever you run the machine learning with the R in the interface, you just run that algorithm. Only change the K or the training set. And now, the other concept is a confusion matrix. Some people are yawning. It seems that you are getting really bored, huh? We're going to end it soon. Look at that. Confusion matrix. Have you heard of that concept before? Yeah? Confusion matrix, it means that how great your algorithm is able to predict based on your training set. The confu mat is a function with the R. Huh? It's a function with the R. It's always there. You only simply put the name of the algorithm inside. And it measures the accuracy. I'm just going to run it. You see a table at the console. At the console, you see a table. At the diagonal, you see 13 and 16 for BCR, ABL, and for the neck. And at the off diagonal, you see 2 and 4. What does it mean? It means that your machine learning. But before that, can someone tell me what is the purpose of writing a machine learning algorithm? The higher goal. The ultimate goal of writing machine learning. Anyone? Any guess?
Make predictions.
Make predictions. That's right. Why you are here? To learn an algorithm to make prediction. Okay? And that's it. It means that the machine learning with confusion matrix made 13 plus 16 correct prediction. But it just made 2 plus 4, 6 incorrect prediction. So this is not bad. It can be improved. We show that later. We can just make it more accurate to have 0 prediction, but that's so far what it is. And now, sometimes you come to ask yourself, I don't like to see the matrix, the table. It's not, I should say, it doesn't tell me anything. It means that 13 plus 16 is 29 correct prediction, 6 incorrect prediction. What does it mean? You come to measure the error rate. I call that error rate KNN. That's a formula. You can always run that like that, and it gives me, what is the rate? 17% per 14. It's the error rate. It's not that bad. Only 17% is a chance that you just make a wrong prediction. Then if our purpose was that, to be like the magicians, to make prediction, we didn't do a bad job. It's good. 17% error rate. It can be improved, but it's still not bad. We met our first goal. Make predictions on cancer genomics. Then you were able on a training set to show the type of the cancer by prediction. But you just go 17% the chance that go wrong. It can be improved, but our purpose is fulfilled. We made a good prediction. Yes, question? No? Wasn't that fun? Yeah? Okay. What time is it? We have almost 20 minutes. I hope that they finish it within 20 minutes. We are just going to run, I should say, I was planning to just cover 3 algorithms for machine learning. You can keep working on those algorithms forever. There is a lot of things to learn. It's a kind of a taster to see if you like the taste or not. It's like, for example, tasting something. If you don't like it, put it aside. If you like it, just buy it more and try it more. Okay, the second algorithm, this is called linear discriminant analysis. For the linear discriminant analysis, you have to use a Bayesian statistics. I'm sure that you think, oh, what an interesting math formula is there. Wow, I like it. I'm sure everyone likes those math formula. That's a Bayesian statistics. If you don't like it, no worries. We do not go there within the next 20 minutes because it takes so much time. I don't know why did I think that 2 hours is enough for every stuff. I was wrong. But anyhow, but for the linear, I should say, discriminant analysis, it makes some prediction based on probability. That's all we know. And sometimes it makes good predictions. That's one of the few, I should say, machine learning algorithms. To run that algorithm, it's very easy. When you run it in the R, you do not need to just go to read many books. You just go to the ML interfaces. You just go to use the function mlearn for machine learning. You know what is the formula? It's going to be your prediction. Your prediction is that thing, the type of the cancer. Tilde dot. It means that the type of the cancer can be the function of anything in my data sets. You imply thousands of variables there. Dot. The data is your data set which you created from your cancer. You know how to prepare that thing so far. You just learned before the break. And the method, look at that, diagonal linear discriminant analysis I. It's always easy. You do not have to do anything. That's the package is already written there. Only you add one I there because you are in the interface environment. And the train IND, it's a training set that you prepare. Then essentially, by this formula in R, with the machine learning interface, you only have to prepare your training data sets, which we did it before the break. Then any type of the cancer which you have, simply use that template, only put your training data set there. The algorithm is written there. The linear discriminant analysis is there, only you just type it there. I'm just going to run it. I call that DLDA1. And this is run. The second thing, you come, okay, let's see the prediction. As a machine learning expert, your job is always to make a prediction. And when you make a prediction, you have to assess if you were right or wrong. And you do that always, remember, with the confusion matrix. You do not have to write anything except to just write that formula, ConfuMat. It's a package already written to assess the accuracy of your machine learning. Then you just go there, only type the name of the functions which you had, Control Enter. Wow, I'm impressed. It seems that we made a bare prediction. Now we have on the data, the diagonal means the correct prediction, 13 plus 17. Your algorithm made correct prediction. But 2 plus 3, the algorithm made a mistake. But how much is the accuracy which you have made? Previously we had 17%. I'm very impressed. Isn't that nice? The error rate which you made with linear discriminant analysis is now 14%. With the KNN, you had 17%. With a different algorithm, you had it improved. So far, it seems to me, without making any improvements, linear discriminant analysis does a better job. Don't you agree on that? There are some techniques to improve it even further, but I'm afraid that we have no time to do that. But stay assured that you can reduce it to 5% to make the accurate prediction. So far, so good? You feel happy now? You learned 2 algorithms for machine learning for cancer genomics, linear discriminant analysis, and KNN. Aren't you happy now? Just only learn as a template, just prepare your data sets, run the algorithm. Okay. Now, I have to just run through that very quickly. One of the purposes, are you okay if you stay 5 minutes more? Everyone's okay to stay 5 minutes more? Because one of the purposes to run, I should say, the workshop was to tell you, when you just work with the cancer genomics, you have a lot of features, and those features is running you crazy. You just want to get rid of that. With the microarray experiments, when you have sometimes hundreds of thousands of the features, not all of them is useful. Huh? You do not need them. You have to identify those features that you do not like them. It's going to be not useful to set them aside. Pick up the ones which is helpful for your analysis and run your experiment with that. Why this is important? Because by doing so, you can improve your accuracy of the prediction. If it got to 14%, if you do, they call that gene selection or feature selection. If you do that, very simply, you have better data sets and you can increase the efficiency of your algorithm. That's the purpose for it. Huh? And that's the thing which I want to do. It was actually one of the main goals for this, I should say, for this workshop. To tell you how to reduce, get rid of some genes, some features, and improve your prediction. Okay? We have two algorithms for it. If you like statistics, like me, and I hope you like it a lot, you can just use, I should say, this function as a t-statistics to pick up the genes which they give you the least p-value. When the genes give you the least p-value in t-statistics, it means that they are the genes which you should fall in love with them. They are the key for your analysis. And in order to do that, you can always use this code as a template. You just route t-test. It's a function comes with the gene selection, with the gene filter. You run it. You order it. You see the order function. And I put decrease, decreasing true. It means that you order the p values from the least to the highest. Then it means that you pick up the, and you just select it. You feature names. It's a function which simply selects those functions. Sorry, I do not explain about them too much. You are short in time, but feel free to email me or just contact me if you need some clarification on that thing. We can just explain that more, or simply do your search on the literature of the t-test for feature selections for cancer genomics. And now, look at that. What did we do? On the training selected, everyone has that code, huh? For gene selected. Now, you have only 50 genes. Look at the last line, train selected on the t-statistics. Do you see it here? 1 to 50. I highlighted there. It means that I only selected out of thousands of features only the first 50 genes. Then I got rid of the curse of dimensionality. And what to do now? I'm just going to repeat my algorithm for K and N. K nearest neighbors. But on a different data sets. I have K, N, and 2. I call that the second algorithm. mlearn function. You should, from tonight, you have to love that function because it does all the job for you for machine learning. The formula is there. Nothing changes. The data sets, you only made a minor change that you put in slicing the data only to the training selected. You only put 50 genes there. And the method is still KNNI with the first nearest neighbor. When you got back home, as a practice, you can change K to 2. You can change K to 3 to find how the error rate changes, because it changes when you change the K. And the training set is where it is. I'm just going to run that function. Let me just put that with 40. For me, it's out of range because I just selected only, I should say, 99% of the cutoff rate. Maybe you can do a better job. Can you run that function? Okay, it just ran for me. I'm just going to run the confusion matrix. And look at that. And I have the error rate. Let's see how much the error rate is that. Originally, wow, what a feat. For the KNN first, when you run it, without gene selection, you had, if you remember, you had the error rate 17%. And now, when you rank the gene, you selected your features, your error rate is now 14%. It makes big, I should say, difference. Still, there are some more room to improve. When you change K, you see that even you can reduce that 14%. And also, we do the second thing. We use the same data sets as a feature selected to run the linear discriminant analysis, which we already got 14%, I should say, accuracy, error rates. I'm just going to run the confusion matrix. Let's see if from 14% you have a better chance to reduce it. Oh, it didn't just work that much well for the linear discriminant analysis. Then the gene selection, it worked much better on the k nearest neighbors than, let's say, on the linear discriminant analysis. That's why a job of a machine learning practitioner is so much fun, because you have to play around, try different things, and analyze them and make the best judgments. Any questions so far?
Are you running confusion matrix on the test set or on the training set?
We run on the test set when we just go to the random forest. Okay, and now, that's going to answer your question on the test set. Okay, I feel a little thirsty. Okay, and now, it is going to be one of the interesting part in the machine learning practices, and that's cross-validation. Who has heard that terminology before? Cross-validation. What do we mean cross-validation? It means that you just run, I should say, your algorithm on the test set. And sometimes you have different approaches. You just divide, for example, they call that k-fold. You divide your training sets on 10 partitions, and for each one you run the test set and you run the confusion matrix and you just sum them up. But the measure which we're going to do here, it's because when you just work with the R and with the machine learning, I should say, interface, it's done for you. How is that done for you? If you just come over there, you define a different algorithm there. Define a different argument. Xval spec means that cross validation specification. Simply, sorry, I had to just go one code above. You just put, I should say, the type of, I should say, the cross validation. I put LOO. It means leave one out. If you just go to the help menu, it shows you different algorithms. Leave one out means what? Every time, for example, you talk about the test set. You run your machine learning algorithm, you exclude one data from it, run your algorithm, and test your accuracy on the thing which is left behind. And you aggregate them at the end. And that's what it means. I'm just going to run it, and I'm just running a confusion matrix, and I see that the confusion matrix is not a little different, but it means that 27 plus 34 correct answers, 10 plus 8 wrong answers. The cross-validation in the whole data sets give you a little bit, tricky, I should say, prediction. You have not a good, I should say, accuracy. Okay, and now we have 10 minutes, huh? Also, when you do cross-validation with leave one out, when you just work on the cancer genomics, you're always interested to also select the features which has more relevance to your analysis. Feature selections. Previously, I did that with t-statistics. You remember those 3 line of codes? You may not like those kind of codes because it's not easy to just run the t-test on each row, then order it, then use the feature names. If you don't like it, no worries. You come here with the xval specification. There is a function, this is called fsfun, equals fs abs t. And I just put a number there. That number does exactly the same thing as we did with the t-test, but here this is automated. It just extracts, for example, the 50 most relevant genes from your, I should say, datasets. You do not have to just do the statistical analysis, the t-test. It's already there with that function. You need, for example, 20 top genes which contribute to the cancer. You have no idea which genes are more relevant and have causal effects for the cancer of the leukemia. That's what we are doing. You just choose 20, and the algorithm for machine learning, while does the cross-validation, finds the most relevant genes which causes the type of the cancer which we are looking for. And I'm just going to run it. I'm just going to do the confusion matrix, but I'm more interested in the third option. Table, unlist, FS history, KNN4. That function, f as history, it's going to give you the name of the genes which you selected. You were looking for the top 20 genes. Has a causal effect. For the leukemia cancer, with the fs history, it gives you the name. And later, we see the symbols of these genes. No need for the t-test. When you just prepare your data set so well, then you can copy-paste the algorithm to find, I should say, the genes which causes a cancer. Okay. And now, let's skip a little. We just go to the last algorithm. We have 7 minutes for the last one. I like that algorithm a lot because it's a very powerful algorithm which is called random forest. I like the name. Random forest algorithm for machine learning. How it works? I just made a very simple, I should say, stuff over there. It's a simple, I should say, demonstration of a tree when it comes to making decision. Look at that. It's a very simple one in order to conceptualize the concepts. You start with a big question. For example, am I hungry? Either your answer is yes or your answer is no. Depending on your answer, you just make another one. Have I $25? I have. I have it. I go to a restaurant. I don't have it. I just buy a burger. I got it from the Wikipedia, but that's the essence of, I should say, a tree, a decision tree. But when you have lots of trees, pack, let's say, thousands of trees together, it becomes random forest. And they have a very high power to make accurate prediction. Okay? And now, we're just going to do the same thing. Don't bother yourself to write the codes. You just go to the machine learning interface in the R. You just write mlearn function. The same thing. The formula. Tilde dot. The data. But for the method random forest, I. But before that, you have to install the package for random forest. It's going to be install.packages random forest. Remember, R is small, F is capital. And it comes with the R, not with the byte-conductor. Then installation is much easier. Just use install.packages. And the library comes for random forest. I'm just going to install it. And this is installed. When this is installed, simply I just go to the machine learning, and you will see that I have random forest I, because I'm just working the interface, and I have training set, but I have two features which I added. This is n-tree, means the number of the trees, because you are working not with a tree, you are working in a forest, and as many trees as you have a better prediction. I just choose 120, I should say, 1,200, I should say trees, my decision making. And mtry, it decides on the relevant genes which you have. That's another feature which you can use instead of using the t-test to find the most relevant genes. I'm just going to also importance, true. Also, you always use that as a template, and everything remains verities. For confusion matrix, wow, look at that. For random forest, on the training set, I used confumat RF1, which was the name of my algorithm for random forest. I'm very impressed with random forest, which it has 1,200 trees for making decisions. I have 0 wrong prediction. Look at that, the power of the random forest. 0 wrong prediction. But if I run it on the test set, I see it's not that bad. I have 5 wrong prediction. It is very reasonable. Okay. And on the next one, I have RF2. The same formula for random forest, but here I have just chosen the number of, I should say, relevant features as 5. We had 50 before, I have 5, but with the same number of the trees. Let's see that number, how it's going to change my prediction accuracy. I'm just going to run it. The confusion matrix on the training set, I'm impressed still. It gives me 0 wrong prediction. But let's see on the train test set, it's improved. I have only 4 wrong prediction. Previously, with the previous one, I had 5 wrong prediction. When I reduced the number of the features from 50 to 5, I have only 4 wrong prediction. That's quite an achievement. And also, as a very last point for the machine learning, for the random forest, we are just going to run, I should say, these 2 packages, which probably some of you had some problem to install it. And by doing that, we are just going to selecting the relevant features. Just going to install the updates. Okay, and just do the library for this. And okay, there is one functions with random forest. This is called get var imp, means get highest variant importance. When you just run that code, it's still installing. And you plot it, the second line, it is going to give you one of the most important things, which was, I should say, the purpose for this workshop, to identify the gene causing to the leukemia cancer. I plotted there. You can always use it as a template, and you will see that I use the symbol there, and it gives you the symbol of the genes which they has the highest contribution, I should say, for the cancer. You can also just use those, I should say, those functions. Those ones gives you, I should say, the best, I should say, the symbols for the genes which relates to the leukemia cancer. And that was one of the important things for the random forest. Then I should say, before we just end, then by the end of the day, now you use 3 different, I should say, classifiers in, I should say, machine learning for cancer genomics, from the k-nearest neighbors to linear discriminant analysis and random forest. And we learned that with the random forest, we have more options to select the features, to identify the genes which relates to the cancer, and also it gives us a better prediction, a better accuracy for the prediction. That was the outcome, I should say, of this workshop, to introduce to you the random forest, that it gives you, I should say, a lot of flexibility. There are, I should say, more packages for let's say, for example, for cancer genomics. One of the most important ones is, I should say, the kernels support vector machines. It's a very complicated stuff. It was not relevant for 2-hour workshop, but I hope that you, we have that workshop coming up. I should say, we are with sponsorship of the OISI. We are running some workshops from the whole month of, I should say, of the August. You can sign up for those workshops. We are working with the Python and also the R to give you some trainings on those ones, that when you start in September, you have worked with all, I should say, algorithms for machine learning, for support vectors, to, let's say, for example, neural networks and anything. When you start in September, you have some, I should say, good understanding of support vector machines. You can just go to the website, and also you can just sign up, I should say, for those coming, I should say, workshop. It's going to start by the first week of the August, finishes by the first week of the September, covers lots of algorithms in machine learning. That's the thing to just finish the workshop. To remind you of 2 things, please go to the website. There is a section for the testimonials. If you enjoyed the workshop, leave some comments there. If you have some feedbacks, leave your comments there. We just improved the workshops, and I hope to see you by the next workshops at the OISI here at the same lab. And I hope that you learned some stuff. I know the machine learning is a very complex, I should say, discipline. It requires practice, and 2 hours, I should say, workshop is not enough. but I'm so glad that it was one of the few workshops in Toronto for machine learning dedicated for the cancer genomics. And I hope to see you again with the next coming workshops. Don't forget, leave your testimonials and sign up for coming workshops starting the 1st of, September. And I hope to see you again. And